morning and welcome, especially you had come last day before Easter. Very nice, thank you. So, let's continue on what we started yesterday, that is the Crank-Nicholson method. We have seen that it is second order in space. Now we want to see that it is also second order in time. And as I told you yesterday, it is easier to do it separately. We can do it at once, but I'll give you a comment on that later. So now just let's consider the part where we look at the time accuracy. So that means we consider now the trapezoidal method. That is for the time integration. And we imagine that we do it for, in our case it would actually be a system of ODEs where we have a time derivative, and on the right hand side we have our residual, let's say. But that is not important now. Important is that how we do the discretization with the trapezoidal method for that. And that is the following. Number 4, that we take the value at the new time level minus the value at the old time level divided by delta t. So for the analysis we simply assume that u is a scalar. We know for us it is a vector, but for the analysis it's okay to think of it as a scalar. And on the right hand side then we simply take the average of the right hand side of our ODE taken at the old time level n and at the new time level n plus 1. So that is the idea of the trapezoidal method. And now we want to analyze that, and we make it simple. We think what will be the truncation error when we insert the exact solution. So that will be the truncation error, and if we would distinguish, it would be the global truncation error. For ODEs we sometimes also actually look at local and global truncation error, but this is the global one. So we say then that the truncation error for this problem is given by the exact solution at the new time level minus the exact solution at the old time level divided by delta t minus 1/2. And now we insert the exact solution here also for u. So that will be the u of t, and it will be a u of t plus delta t there. So that is then our analysis. And then, since we are inserting the exact solution now, we can use the ODE. So that means we can use here, by the ODE, this is equal, say, let's see, I take it simply as u prime, first derivative. So we use now the ODE. So that is here, that is our ODE. So that we can use here. And likewise here, that is just at the new time level. Again, we use the ODE, and that is then the u prime of t plus delta t. And then we can do Taylor expansion, and we find then that the truncation error is, we do first for u. I skip now the t, it's all at, we do the Taylor expansion around t. Plus delta t u prime plus delta t squared half double prime, and I take also the next one, delta t to the power 3 divided by 6, third derivative, plus higher order terms minus u from here divided by delta t. So minus 1/2 then we don't need to do anything here. It's just u prime of t plus, now here we do now Taylor expansion of u prime around t. So that will give us u prime plus delta t u double prime plus delta t squared times the third derivatives plus higher order terms. So, and now we can simplify things a lot because the u here cancels and we have the u prime delta t, so we get from this here already, we get that this is equal to the u prime that is left here, and then the next one will be delta t half u double prime, and we'll get I take also the next error term, third derivative plus higher order terms. And on the right hand side we can summarize, oh here I take the, well I didn't need it, it's not wrong. So that is the u prime is double, so we get it 2 times, so that together we get then u prime. And here from there we get then delta t half u prime double prime plus, and here from that we get then delta t squared divided by 4 times the third derivative plus higher order terms. And now we see that the u prime and the next term, they cancel. So we see here this and this term, they cancel with that. And then we are left with 1 over 6 minus 1 over 4 delta t squared times the third derivative as the leading error term. So from that we can then see that the truncation error is equal to, that is 1 over 6 minus 1 over 4, that is minus 1 over 12 times delta t squared third derivative plus higher order term. So that means our truncation error is of second order. So that means the conclusion from that is that the trapezoidal method is second order accurate. So that was what we wanted to show. And then together with what we showed yesterday, then when we use the Crank-Nicholson, we use then actually the trapezoidal method in time. So then we have, by the Crank-Nicholson method, a second order in time. We showed already that it's second order in space. Altogether, Crank-Nicholson method is second order in space and time. And that concludes then the consistency analysis, because then the method, if it is second order, it is clearly consistent. Because then the truncation error will go to 0. Here we see it very easily as delta t goes to 0, that goes to 0. Regarding the remark that I mentioned in the beginning, we could have done this in the usual way by simply writing the truncation error directly for the Crank-Nicholson method. That's possible, but that is a little tedious. Let's see. Well, I can show you just this page. It's very tightly written, and there are a lot of Taylor expansions, and the problem is you have to do it around with 2 variables. So it's with t and x, because if you have the, say, the u n plus 1 at j plus 1, then you have to do Taylor expansion with respect to x and t at the same time. It's no problem, but it gets lengthy. So it can be done and the result is the same. So therefore that's the reason why we took it in this way, which is simpler. So then we have accomplished consistency, and now we focus on stability. So that is the second part, stability. And the Crank-Nicholson method that we are discussing for the heat equation, that is the number 1 of yesterday, that can be expressed in the following way. Let's see, that is 5 for the truncation, error in time. Let's take this as 6. So we bring now everything that is on the new time level on the left-hand side of the equation and anything else on the right. We have multiplied by delta t, and then we get the following: the ujn plus 1 minus, and when we multiply by delta t, we get alpha delta t divided by delta x squared, that is the r. I mentioned that, well, before forgetting it, I just write it. R is sometimes called the von Neumann number, the alpha delta t divided by delta x squared. Alpha is the thermal diffusivity in the heat equation. So then we get here the r half, actually, because we have the half is coming from the averaging between the old and the new time level. And then we have here what is then coming from the discretization of the second space derivative at the new time level. So that is then this, all at the new time level. And that is then the usual from the second order discretization of the second derivative. So that will be on the left-hand side, and on the right-hand side we have then the uj from the old time level. Now here we get then the plus r half, and then we will have similar expressions as we have there, just at the old time level. So let's complete that. Uj plus 1n minus 2ujn plus uj minus 1 minus 1n. So then we have this form that is then suitable to do the stability analysis. What we do is, as usual, with the von Neumann stability analysis, that we insert a Fourier mode. So what we do, just to remind you what we are doing, is the von Neumann stability analysis, sometimes also called the Fourier analysis. And that is, we imagine that we can decompose the discrete solution in a finite sum of Fourier modes. And since these modes are linearly independent, we can just focus on one. So we insert one Fourier mode, which we denote by its amplitude, or the Fourier transform u hat k, so that is for wave number k, e to the I k xj. Xj is grid point xj. We insert that Fourier mode for the discrete variable uj into the Crank-Nicholson method, written as 6. So if we would do that also with a time level, we could also include the time level n here. Then we have all what we need. We insert that into equation 6. And then it is just a matter of writing what and using the fact. Yeah, it is simply straightforward. Let's just do it. So we have uj n plus 1, then the amplitude is at the new time level, e to the I k xj, minus r half, and then we have u hat k n plus 1, and e to the ik, now we have xj plus 1. So we have this term here, the next one, minus 2, u hat kn plus 1, e to the I k xj, and then we have the ujn, uj minus 1 n plus 1, so that gives us the full mode at the new time level, e to the I k xj minus 1. So then we have taken into account the left-hand side, and then we also for the right-hand side. And we get uk hat n plus r half, and then we have similar expression as we have here, just at the old time. U hat kn e to the I k xj plus 1 minus 2 uk hat n e to the I k xj plus u hat kn e to the I k xj minus 1. So then we have taken everything into account, and now we simply observe that we can cancel the e to the I k xj everywhere, and we use in here that, so we use here that the xj plus or minus 1, we can express that as xj plus or minus delta x. So then we can, for example, express this here as e to the I k xj times e to the I k delta x. So that is now used, so we divide by, divide by e to the I k xj, the whole equation. And we factorize then the amplitudes at the same time, and then we get, so this is then gone, and we get simply a 1 because we factorize that, minus r half, and from here we'll get then the contribution e to the I k delta x, because we divide by e to the I k xj, and then it is then plus delta x, but that can be expressed as times e, this factor. Minus 2, that can be done directly, and from there we get then e to the minus I k delta x. Because here we have xj minus delta x. So then we have this on the left-hand side, and we have factorized the amplitude at the new time level. On the right-hand side, we do a similar. We have here the beginning thing. Let's see, I think here I forgot something. Sorry for that. Now I see it. I forgot here, but it's not a problem seeing it. I forgot here. I forgot here simply the factor e to the I k xj. So that should of course be also here. I simply forgot it. Here it is okay. And we divide by that, and we factorize this, so we get from that we get a 1 plus r half, and then here we can repeat what we have there, e to the I k delta x minus 2 plus e to the minus I k delta x. And then we had factorized the u k hat at the old time. So, and from that we can now easily determine, well, first we make a little simplification, because we have here terms, actually they are the same, on the left and right hand side involving e to the plus and minus I k delta x. So there we use Euler's formula. Euler's formula gives us that e e to the plus minus I k delta x. That is equal to the cosine, and for the cosine the plus and minus doesn't matter, k delta x, but for the sine it matters. Plus or minus imaginary unit I times sine of k delta x. So if we use that, we see easily that if we add these exponentials, then the imaginary part vanishes and we get 2 times cosine. So that is here on this side, it's the same on the other side. So then what we get out of this here is then 2 cosine of k delta x minus 2. And then we can also write this cosine k delta x, so we can factorize the 2 here. So that is then 2 times cosine k delta x minus 1. And that, again, we can use a binomial formula to get that as minus 2 sine of squared of k delta x half. So that will then make things even more compact. And in the end we get then here a minus 4 sine squared of k delta x half. So you can see that. So then we have simplified these expressions in parentheses, and then we can write the amplification factor in a bit more compact form. So, knowing this, well, already from this expression here, we can get the amplification factor. So the amplification factor becomes and that is then 7 denoted by g of k delta x. It's dependent on the, we could say, non-dimensional wave number, the wave number times the grid spacing. And that is defined as the ratio of the amplitude or Fourier mode at the new time level and the old time level. And then we see, so when we divide by this, then we have it on that side, and to get this form we have to divide by this. So we get then this in the numerator, we get this here in the denominator. So we get then 1 minus, and now we use the simplifying expression. So this, what in parentheses is minus 4 sine squared k delta x half multiplied by r half. So that gives us the minus 2r sine squared of k delta x half. And in the, so that is, sorry, that is wrong. Let's see, I have to check here. My things, no, it must be plus. Because we have this, and here we have a plus. Let's see. Yeah, that is, let's see, I have to check things here. No, we have a minus in here. I forgot the minus. Let's see here, this minus here, that turns the sign. So that means we get then, on this side we get then here a minus. It was originally correct. Sorry for that. Now we know why. So again, in parentheses, this is minus 4 sine squared and then this turns it into a plus. 1 plus 2r sine squared of k delta xr. So that is the amplification factor. And the criterion in the von Neumann analysis for stability is that the absolute value of the amplification factor has to be smaller equal than 1. This simple dependence. So then we simply have to check that to find the condition that will impose on R, if any. So then, the stability condition. And that is that the absolute value, if we now introduce this, the beta for the k delta x, that has to be smaller equal than 1 for all beta. Interesting ones are for up to pi. Then we cover essentially all, and we assume here that the beta is k delta x. So that is what we want. And then it is now a matter of looking whether the amplification factor is real or complex. When it's real, then this, in our case it is real, so in our case the g of beta is real. Then it means that we have to have this between -1 and +1. That is the condition. If it would be complex, it's easiest to compute the modulus squared, which we get by computing the real part squared plus the imaginary part squared. We had also examples of that, but here it is easier. It is just real, so we have this condition here. And that is then equivalent in our case, if we look at this form, then we can multiply by the denominator, and let's assume that we take that the denominator is positive, which is the case if r is positive. So then this is equivalent to -1 plus 2r sine squared beta smaller equal than, that is then the numerator, 1 minus 2r sine squared of beta. Then we have multiplied, so it becomes in the plus on the right hand side, 1 plus 2r sine squared of beta. So if we look at the right hand side, then we see that we can take away the 1, and then we see that we get -4, so this we can write it. And we see this is equivalent to saying that -4r sine squared of beta is smaller equal than 0. So that is clearly okay if r is greater equal 0. The only thing that makes sense, because that's defined by the thermal diffusivity, and that has to be positive to get a well-posed problem. Sorry. Yes. You're right. Thank you. Good point. I missed the half. Good point. We have to correct that. So that's exactly right. Everywhere I correct it. Good, thanks. So then we have also it off. Good. Now we have it. So then the argument is, or still okay. So the R, the phenomenon number has to be small or equal than 0, so then this is okay. On the left-hand side, we see with the minus here, this vanishes, and then this here is equivalent to saying that minus 2, or you can take it as it is, minus 1 is smaller or equal than 1. And that is clearly okay, so the left inequality doesn't give anything. But the right inequality says that R has to be smaller, greater or equal to 0. So from that we can conclude that the Crank-Nicholson method is stable for all R larger or equal to 0. So, or we call that also unconditionally stable. So the Crank-Nicholson method is unconditionally stable. And that means stable test, stable for all R greater or equal to 0. So we can choose the time step as we want. So that is the, but the main point is it is stable. So then we have accomplished earlier consistency, now we have accomplished stability. But before we then conclude also convergence, we want to investigate a special case. That was in the beginning of the, yesterday I told you the question, can we use this method when we take a large R? We know from Euler, implicit Euler, we can do that. But what will we get here with the Crank-Nicholson method? So let us look then for the limit when R goes to infinity of G of beta of our amplification factor there. So that is then the limit from R to infinity. And then we write this ratio 1 minus 2R sine squared beta half divided by 1 plus 2R sine squared beta half. And then we see when beta is 0, the sign is 0 and we get 1. So that is an exception. But if beta is not 0, and for us the interesting range is here up to pi. So if we take pi as the limit, pi half sine is 1. So we get something here. But if we let R go to infinity, then this is dominating. So we can then divide by 2R sine squared beta squared half. And then we see that we get here a minus 1 that is dominating over this, because this is the 1 divided by R something, divided by plus 1. So that means the limit is minus 1 when we let R go. And we assume here that beta is not 0, and for us pi, 2 pi is, pi is okay, but 2 pi is, we don't look at that. So that means that the amplification factor is shifting sign. At one time step it is minus, the next we have plus, so it's each time it's changing sign, and that means oscillations. So that means when we have this situation, we can expect that the waves representing our solution are oscillating, because they flip from plus to minus, like this. Remember, the amplification factor means that we multiply in each time step the solution by this. So the wave amplitude of some wave is each time multiplied by this factor. If it's minus 1, it means that the amplitude is flipping. It means oscillations. So that means that we can expect oscillations. So the numerical solution that is then true for all waves except for the wave with the wave number 0. So the numerical solution for all wave numbers k except for k equals 0 will oscillate for large r. So therefore, we should not use it. It's not a good idea to use it for large time steps, for large time set or large r. So what you should rather use then is the implicit Euler method. That works fine. That has not this problem. Okay. Let's see. Go to the very limit here, so it's not that large r, but I get clearly some problems. That is with the Crank-Nicholson method. So there is it's behaving strangely. So it's not oscillating, but it's giving. We could imagine it is near the boundaries. We get here some strange values. And that is already for R 1000, and I did not go here to steady state in this case. So the corresponding values for the implicit Euler method, I give here some more information that is not important here. The important thing is here, let's see. The red line is the exact solution at that time, and the circles are the numerical solution with the implicit Euler method. So it is at least closer to the exact solution, and we do not have this overshoot or this going beyond 1000, which is the bound here for it's a heat conduction problem that we saw for the Crank-Nicholson method. And with that, it is no problem to take. I took the R, the phenomenon number 10 to the 20. It's no problem with the implicit, but with the Crank-Nicholson, it does not work. So I get strange results. Okay, so that means that we can use then this method for transient problems when we need time accuracy, because it is more accurate than the implicit Euler method. But for getting steady state, it is not suitable. Then we should rather use the implicit Euler method. Okay, so then now we want to conclude looking at convergence. Because we have now established the stability before we have really established consistency. Now the last point that we have to conclude, that was also the question, is convergence of the Crank-Nicholson method. For doing that, we have already mentioned in the beginning, yesterday, what we need here is the Lax equivalence theorem. That tells us if we have a numerical method for an initial value problem, a linear initial value problem, that is consistent, then stability and convergence are equivalent. So that is simply now to conclude. So that is the third point, and that is convergence. So the argument is, as the Crank-Nicholson method, that is our equation 1, is consistent. We actually should show that it is second order, but it would be okay. Just consistent means that truncation goes to 0 as delta t and delta x go to 0. And we showed also that it is stable for all phenomenon numbers are greater or equal to 0. Then it is, as I just said, the Lax equivalence theorem that yields then also the Crank-Nicholson method is convergent under the same restrictions that we have, and the only restriction is that R is greater than equal than 0. So then we have established convergence. And that means, as we remember, that the solution, the numerical solution of the Crank-Nicholson method converges towards the exact solution of the heat equation. That is what we want. So, that is an example of consistency, stability analysis, and then concluding with the Beck's equivalence theorem also on convergence. Do you have any questions regarding this part, regarding consistency, stability analysis, convergence analysis? We had a couple of examples on that, and you can also expect that in the exam. So that is something that you should be familiar with, so that you can do both consistency analysis using Taylor expansions and von Neumann analysis by plugging in Fourier mode and knowing a little bit about the use of complex numbers to find out under which conditions, first find out the amplification factor, and then under which conditions the absolute value of that is smaller or equal. Okay, if you have not any questions at the moment, but please ask me if you get. I want to state the next problem, which we then will discuss the solution after the break. And that is something I consider interesting in itself for many applications, and it is called Richardson extrapolation. So the problems, I want to state two problems, but they are very much related. We suppose we have suppose you have determined, that means you have used some, in that case, some ODE method, and determined the approximations. And I shall now introduce a notation that is the following. I call it y delta t of t. And what I mean by that is it's a numerical method to compute an approximation of an ODE at time t using the time step delta t. So then we have one approximation obtained with delta t, and another one we have obtained with delta t half. So that's what I mean by that. But we determine the solution at the same time, and that is then of some ODE that it is an ODE, it is an initial value problem. That is what we do here. And that is then y prime is equal to some given right-hand side, ty, and we have some initial condition, y0. So that is our ODE problem. And we have done that then, as I already said, with time steps delta t and delta t half. So that is what these denote. And t is some finite time. Now we make an assumption. We suppose that the global error that is, we looked at it in the beginning, that what we call the truncation error for the ODE, so we consider the global error is of order p. For example, trapezoidal method, order p equal to 2. And that the next order is r. Next order r. So, and that means we assume the following. We assume that we can express the approximation at the time t computed with the time step delta t, that this error with respect to the exact solution, that is y of t. So y delta is the numerical solution, the approximation, y of t the exact. We assume that this is equal to some constant, we call it here a1 times delta t to the power p plus an order delta t to the power r, and we clearly have that r is greater than p. In probably most cases, r is simply p plus 1, but we have cases also that what we considered where trapezoidal method where we have r is p plus 2, so 4 in our case. P is 2 and r is 4. And the question is, how can you get a more approximation of the exact solution having these two approximations? That is the question. So how can you get a more accurate approximation of the exact solution of the ODE at time level t using these two approximations? Okay, so that is the question, and the other question that we shall also address after the break will be very similar argument. Suppose you have numerical solutions for an ODE that you have computed not with delta t but with delta x, and the delta t is related to the delta x by the current number for a hyperbolic problem or by the von Neumann number for a parabolic problem. So suppose you have then solutions with delta x and with delta x half for some point in space and some final time t. And then the question is the same. Well, you have also then given something similar, that the error can be expressed then in a similar form as this, but not with the delta t but with delta x here also. The question is then, how can you get a more accurate solution? So that we'll then look at after the break. So 15 minutes.